Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. In 1982, astronomers confirmed the presence of a multiple planetary system orbiting a pulsar located about 2,300 light-years from Earth. This constituted the first confirmed discovery of planets beyond our solar system. Since then, 5,084 exoplanets have been confirmed in 3,811 star systems, with an additional 8,912 awaiting confirmation. With so many exoplanets available for study, the process has transitioned from discovery to characterization, where astronomers are beginning to rely on next-generation instruments, techniques, and improved data analysis to look for potential evidence of habitability, and even life itself. In the coming years, even more sophisticated instruments will allow them to probe further and directly observe exoplanets for the chemical signatures that we associate with life. I'm Matt Williams, and welcome back to Stories from Space. Today, we're discussing exoplanets and the way in which the field of study has exploded in recent years. To say that we've come a long way in a short space of time would be a massive understatement, because astronomy has undergone multiple revolutions in the past few decades. It's really quite amazing the way that the pace of discovery and learning has advanced by leaps and bounds. To think that it was just 30 years ago that the very first exoplanets were confirmed, and detections had been made prior to that, or at least what was believed to have been detections, but these remained unconfirmed. And then between 1992 and the late 2000s, there were a few dozen more cases of exoplanet detections and a few confirmations. But with the deployment of the Kepler Space Telescope in 2009, we entered into an entirely new age in the field of exoplanet studies, where it really emerged in its own right, and scientists were adding hundreds of new detections with every passing year. And the confirmation process rapidly sped up as well, so that by 2015, we were well into the thousands of confirmed exoplanets available for study. And in terms of methodology, where the methods that have proven most effective, that has been making something of a transition as well. Up until now, the only reliable way of detecting exoplanets was through indirect methods. The most popular of these is known as the transit method, and this consists of astronomers viewing a field of thousands of stars and gathering light from them, and they're measuring what's known as a light curve, where the light coming from a distant star experiences rises and falls, and if you view it on a graph, it looks like a waveform or a curve. And noting periodic dips in that light curve, that is what tells you that a planet may be orbiting there. And specifically that a planet is orbiting edge-on relative to you, the observer. And whenever it makes a pass in front of the star relative to you, or a transit, there will be a corresponding dip in brightness. And if that is a periodic thing, if it happens consistently, then astronomers can say with confidence, yes, there's an exoplanet there. This is its orbital period. And from that, they're also able to obtain estimates on its size, how close it is to its star, and how many days or even hours, depending on how close it is, it will take to orbit its parent star. So this method has therefore been very reliable at detecting exoplanets and also confirming them. But it does have some drawbacks. For example, you need to be able to see these planetary systems edge on, or otherwise you're not going to be able to detect them. And second of all, this technique is really only effective when dealing with brighter stars. So when it comes to cooler stars, red dwarfs, they are by far the most well-represented class of star in the galaxy and in the universe at large. They make up 75 to 80% of stars in any given galaxy. So when it comes to them, they're far too dim to get an accurate return using the transit method, at least using instruments to date. So a second highly popular and very effective technique that's been used is known as the radial velocity method, or Doppler spectroscopy as it's called. And in this case, you observe cool red dwarf stars using what's known as a spectrometer, which analyzes the light coming from it and breaks it down into different colors of the visible spectrum, and is monitoring the star for what's known as redshift and blue shift. And what this means is that the light you're seeing is shifting to either the blue end of the spectrum or the red end of the spectrum, which indicates that it's moving closer to you or farther away. And measuring that change over time is basically you're measuring its radial velocity. And this is the same way that astronomers measure how fast galaxies are moving away from us or towards us. It's how they've been doing it since the time of Edwin Hubble, who confirmed that most galaxies in the universe were expanding away from us, thereby demonstrating cosmic expansion. In this case, however, what you're seeing with an individual star, this is the result of gravitational influences on it, which can confirm the existence of a planetary system. And by measuring the radial velocity of individual stars, scientists are able to determine just how massive these planets could be. So, whereas the transit method is very good at detecting exoplanets and constraining their size and orbit, the radial velocity method is very good at constraining the mass of planets. So, when combined, these two techniques are very good at determining the size, the mass, and the distance of a planet from its star, thereby giving you some idea of whether or not it's a rocky planet or, say, a gas giant, whether it's too hot or too cold, and whether or not it basically fits the parameters that we associate with life. So a rocky planet orbiting just far enough from its sun that it's in the quote-unquote Goldilocks zone or habitable zone, where water could exist on its surface and where an atmosphere could remain stable. Now, to date, these two methods have confirmed the vast majority of exoplanets in our universe. But as I said, there's a transition going on where we are moving from indirect methods to more direct ones. So, for example, you have a method known as gravitational microlensing, which is a variation on gravitational lensing, where astronomers will use a massive object like a galaxy or galaxy cluster as a lens because of the way their powerful gravitational forces will cause light from more distant objects to bend in their presence and be amplified. And this is the effect that gravity has on spacetime, where it alters its curvature and what was predicted by Einstein's theory of general relativity. And the same holds true of gravitational microlensing, where astronomers will use a parent star as a lens to amplify any reflected light that's coming off the planet as it's orbiting behind it. And this method is very much in its infancy, and only 130 exoplanets have been detected so far, but it's especially exciting for astronomers because it will become much more widely used in the coming years, thanks to next-generation instruments. There's also a method known as astrometry, which consists of measuring the position and proper motion of stars as they orbit the center of the galaxy. And by doing this, astronomers can detect any apparent signs of wobble. And similar to the radial velocity method, this is interpreted as indications that gravitational forces are acting on it, which could indicate the presence of planets, and thereby discerning just how massive they are. Even more exciting is the way direct imaging will be possible thanks to increasingly sophisticated and sensitive instruments. And in this particular case, as the name suggests, you observe a star, you look directly at it, and then you try to spot small point sources of light around it, which is a system of planets that are reflecting light from their surfaces and their atmospheres. Now, ordinarily, with regular optical telescopes, the brightness of the star itself is many, many times brighter than any light reflected from the planets, so it obscures that light. But using instruments like a coronagraph or starshade, which block out the light of the star itself, you're then able to see these little point sources of light clearly. And in the coming years, next-generation telescopes like the James Webb telescope, which will be followed in a few years by the Nancy Grace Roman telescope, and several ground-based telescopes like the Extremely Large and the Giant Magellan and the 30-meter telescope, they're going to be equipped with their own coronagraphs with advanced optics. Ground-based telescopes will use adaptive optics to correct for atmospheric distortion. This will allow them to directly image exoplanets like never before. And what's especially exciting about that is that astronomers will now be able to see the light coming off of a planet's atmosphere And they'll be able to characterize it, again, using a spectrometer, which will divide the light into the visible spectrum, and from that, they'll be able to see exactly what chemical elements constitute it, because, as scientists have known for centuries, different elements absorb different wavelengths of light, and then they radiate it out at other wavelengths, and that is basically why we see colors. And so by looking at reflected light through a spectrometer, astronomers will be able to say, yes, this atmosphere is composed of things like nitrogen, oxygen, carbon dioxide, which are all very good indications of habitability and maybe even life, because that is the situation here on Earth. And so this method will allow for exoplanet characterization, which is to say potentially habitable or not, like never before. And up until now, that's been very difficult. As we said, the means for determining whether or not planets exist or are potentially habitable had been largely indirect. And the reason for that had to do with the limits of our instruments so far, and so it was really only possible to detect particularly massive planets that orbit a great distance from their stars, so we're talking about gas giants. So while we would be able to see them directly and study them directly, scientists do not believe these have any chance at supporting life. And while astronomers have been able to then gather spectra from their atmospheres, it largely confirmed what we already suspected based on gas giants here at home. They're predominantly made up of hydrogen and helium and other trace elements, and there's going to be tremendous heat and pressure in their interiors, and not a good place to be looking for life. Certainly not any kind of life that as we understand. And other methods besides direct imaging, they're really not good at obtaining spectra from exoplanets, except for the transit method where, on occasion, you see a planet passing in front of its sun. Light passes through the atmosphere relative to the observer, and the astronomers, if they can get a close enough look, they'll be able to examine that spectra and determine what gases are there. But again, this has really only been possible with gas giants so far. In particular, hot Jupiters, the ones that orbit particularly close to their suns and are very massive and gaseous and even experience metal rain in their atmosphere. But with James Webb, Nancy Grace Roman, and the ground-based telescopes, as I mentioned, the astronomers will be able to find smaller, rocky planets that orbit more closely to their stars. And that is precisely where we expect that potentially habitable Earth-like environments are going to be found. But there's also the wider search for life, which we now refer to as astrobiology. It's not just for life as we know it, but life in general. The life as we know it approach is known as the low-hanging fruit approach, where we're looking for chemical signatures that we associate with life because we know how to look for them. More exotic life, on the other hand, the kind of stuff that's possible, is to us still just the stuff of theory. We need to test those theories. We need to test all the theoretical predictions about what kind of conditions life could exist under. And right now, there are a few ideas. A more popular one is the idea of methanogenic life, which is very much inspired by Saturn's largest moon of Titan and what we've learned about this environment in the last few decades. Basically, Titan has an environment that, despite being very, very cold, is strangely Earth-like in some ways. It's got an abundance of prebiotic conditions and organic chemistry and organic molecules, and this largely takes the form of methane. What's more is that methane on Titan is what water is on Earth. It has a cycle. It exists in the form of gaseous clouds in the atmosphere. It has precipitation where liquid methane rains down on the surface and is held there in the form of methane lakes. And typically one would not think that this would be conducive to life. But again, we have to assume that there is life as we don't know it out there. And if the basic building blocks are all there and the right chemical processes and precursors to life are there, could there actually be life? Even if it's just in a very simple form. And we just don't know yet. We haven't been able to investigate this theory, but there are missions proposed to go to Titan, such as the NASA Dragonfly mission that is going to investigate that more closely. Similarly, there are many other moons in the outer solar system that scientists believe are actually a more likely place to find life than, say, Mars, which is the focus of all of our astrobiology efforts right now. So, looking out into the universe there, we may find that we are looking in entirely the wrong places. Maybe we should be looking at exomoons rather than exoplanets. Or rather than looking for planets with nitrogen and oxygen atmospheres, we should be looking for ones that have hydrocarbon atmospheres. Instead of following the water, maybe we should be following the methane or the ammonia. And similar theories have been said about silicon-based life. It's the same minerals that make up so much of the material in the universe, and perhaps under the right conditions, they could give rise to silicon-based life forms. So yeah, the goal has always been the search for life and really determining the answer to the age-old question, are we alone in the universe? And this all used to be known as exobiology, but it is now known as astrobiology, because if we are looking for life in general, then that includes, as we know it here on Earth, but under different chemical conditions, different environmental conditions. We're not simply talking about foreign organisms, which is what exobiology means. So, much like our instruments, this too has been a limiting factor. Our frame of reference has been very limited because humanity only has one example of a planet where life exists and only one set of chemical domains and regiments. We're really only familiar with the evolutionary pathways we've seen here. But in that respect, too, we're also limited because there really is so much about life here on Earth that we don't know yet, that we still need to investigate. And much the same is true about intelligence. When we are looking for life in general, we're referring to anything from simple to very, very complex. But if we're talking about the search for extraterrestrial intelligence, which is to say intelligent life that we would be capable of communicating with, presumably because they rely on technologies that leverage the same physics that ours do. Well, here too, what do we really know about intelligence and how it comes about? We tend to assume there's such a thing as convergent evolution that would favor cerebral development, frontal cortex development, that would give rise to a species that similarly is reliant upon tools and manipulates their environment to ensure the survival of their species in greater and greater numbers. But yeah, we're very much projecting humanity, that which is the only example of a civilization that we are familiar with. And there's a lot of evidence to suggest that there's countless examples of intelligence in the animal kingdom, whether it's tool using, whether it's agriculture, or whether it is just the brain capacity of a creature. In fact, we've even found that in certain species of ants, they do practice a form of agriculture, and they have a hive-like intelligence going on there. So these are all very, very complicated questions. So there too, our frame of reference has to expand in order for us to be more successful. And this is perhaps the truest paradox when it comes to the search for extraterrestrial intelligence. This is the real paradox behind Fermi's question. It's that we can't find what we're looking for unless we know how to look for it, but we won't know how to look for it until we find it. So all we can really do in the meantime is, as I said earlier, is the low-hanging fruit approach. Follow the water, follow the oxygen, nitrogen, carbon, and follow the methane. These are what we would refer to as biosignatures. They're associated with life as we know it, or they're byproducts of life as we know it. And in terms of technosignatures, or signs of technological activity, there too, we're constricted to the low-hanging fruit approach, where we've been looking so far only for radio transmissions, because we know that that is a viable technology. But of course, there's multiple theories about, well, what about neutrino transmissions? What about directed energy? What about gravitational waves and all these others? So we have a theoretical basis to cast a wider net, but we need to test these out, and we do need to wait upon some further developments before we can truly test them. The exciting thing is we're now at a point in our technological development and in our development as a species in terms of what we're prepared for, what we can conceive of. We are now at a point where we're prepared to take a whole new leap In the meantime, we'll be looking for Earth analogs. We'll be looking for life as we know it in terms of biosignatures, and we will also be looking for signs of technological activity as we know it. And the odds of us finding any or all of this are going to increase considerably in the coming years because our methods and our instruments will be vastly improved. And astronomers expect that within a few decades, the census of exoplanets is going to have expanded because thus far, of the 5,084 confirmed exoplanets, 1,777 have been Neptune-like, which is to say smaller gas giants. Another 1,579 have been super-Earths, which refers to rocky planets that are several times the size and mass of Earth, and 1,535 have been gas giants in the Jupiter-sized range. Meanwhile, only 188 have been terrestrial, which is to say comparable in size and mass to Earth, whereas 5 have defied classification so far. So far, the vast majority of exoplanets that have been confirmed have been giants. Now, this reflects the limitations of our instruments so far. Obviously, planets that are larger are going to be much easier to detect, and astronomers expect that between James Webb and the Nancy Grace Roman and dedicated 30-meter or more aperture ground-based telescopes, plus next generation space telescopes, that this census is going to change considerably. We're going to find thousands of more terrestrial planets, and so the odds of us finding a Earth analogs is going to be much greater. And by the 2040s, 2050s, in fact, it is considered a safe bet that we will have found the first indications of life beyond Earth, certainly beyond our solar system. We may have found indications of life beyond Earth within our solar system by then, too, thanks to missions like Dragonfly and the Europa Clipper and JUICE and a possible Europa Lander or Enceladus Explorer. And so discoveries that we make within the solar system, these are going to help inform surveys beyond the solar system. With a much more full census of exoplanets out there, we're going to finally be able to answer a very burning question, which is the solar system, is it representative of what exists out there, or is it a bit of an outlier? And that's something that astronomers have been just wrestling with for decades. And all of this is going to be happening within just a few years. We already have the James Webb Telescope providing us with the most detailed and breathtaking images of the universe yet. It has already yielded spectra on exoplanet atmospheres, which was a demonstration, really, of what it could accomplish. And very soon it'll be turning that high-resolution imaging towards rocky exoplanets that could very well be perfect Earth analogs or super habitable planets. And there's no guarantee that we're going to find anything out there. There's certainly no guarantee we're going to find examples of civilizations out there. But the fact of the matter is, we're going to be finding out soon. Or at least, at the very least, we're going to have a much better idea. And that is something to be very excited about. Equally important, there's no shortage of candidates that we'll be looking at in the coming years. The James Webb time has already been set aside for it to examine exoplanets right next door in Proxima Centauri, the 7 rocky planets in the TRAPPIST-1 system, and countless other Earth-like planets. And if and when and where we find life out there, this will provide us with a far greater frame of reference for searching for life in the universe. The burning question, is humanity alone in the universe? Is there life beyond Earth? Is there life beyond our solar system? We're not going to have to wait much longer to find out. So until next time, this has been Stories from Space. I'm Matt Williams. Thank you for listening.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.